Okay, good morning. So we continue looking at the strength in behavior of masonry under different actions. We were examining the behavior of masonry under compression and trying to look at the possibility of a closed form solution that gives you the compressive strength of masonry with a knowledge of its constituent properties, the unit and the mortar. And the theoretical framework that we were looking for failure under compression on the basis of linear elastic, an assumption of linear elastic behavior of the constituents was what we were looking at in the previous lecture. And we were examining, as we were concluding the lecture, how this important assumption that the constituents are behaving in a linear elastic manner actually does not explain completely the failure mechanism as physically observed, right. So, the Haller-Francis theory, which is what we actually defined, neglects this nonlinear behavior that you should expect of the constituent materials. And the point is, if it is linear behavior that you are going to be assuming both in the unit and in the mortar, it is going to be difficult to explain how the failure in the brick and the crushing of the mortar actually happen as simultaneous phenomena in reality, but the theoretical framework developed in this manner would not be able to give a justification for the physically observed phenomenon. So, therefore, developments on the further developments in this direction have actually examined the possibility of looking at an inelastic behavior of the mortar. This becomes an unrealistic, the linear elastic assumption becomes an unrealistic assumption both for situations of the brick unit failing first or crushing happening in the mortar early on. So, this slide that you can see is where the unit has reached a level of biaxial tension that causes cracking, following which is where the crushing of the mortar is expected to happen. However, if you are looking at very weak mortars, then as per this theory you should have crushing in the mortar that happens quite early on, and the failure in the brick unit that happens after, which again does not really explain the physical phenomenon of coaction between the two. So, you see the disparity in the values of F and D which do not give us clarity on how physically the phenomenon is occurring, with the cracking in the brick unit leading to loss of confinement in the mortar, causing crushing failure in the mortar itself. So, the extension that we will look at, which is useful to examine, is one where we consider that the mortar behaves in an inelastic manner. Now, between the mortar and the unit, you will agree that the behavior of the unit is, being the brittle material, probably closer to a linear response, and it is okay to consider a linear elastic behavior there, but look at a nonlinear behavior and an inelastic behavior of the mortar itself. So, we are looking at the basis of this approach is the Hilsdorf's approach of 1969, and if you remember the initial slide that I showed you when we were looking at coaction between the two, the mortar and the unit, is where the stress path in the unit also has a inelastic behavior. The stress path of the mortar and the prism also has inelastic response, and you can see that it is almost a simultaneous occurrence of failure in both the unit and the mortar. Okay. So, if this is really the more appropriate basis to describe a theoretical framework for the failure, then what is important is that you have an analytical form of the failure of the unit and an analytical form of the failure of the mortar, and considering factors of compatibility and equilibrium, be able to use these two and write the final expression. So, that is exactly what we will be looking at. So, the condition under which the unit is going to split, we looked at this earlier, the straight line failure surface between uniaxial compression and uniaxial tension in the brick masonry unit itself. If you are looking at the axial compression, which you can estimate the axial compressive strength of the brick unit, uniaxial compressive strength of the brick unit from a flatwise compression test, and you get FBC, the uniaxial compressive strength of the brick. You do a direct tension test on the brick unit and establish the direct tensile strength of the brick unit, and it is a straight line failure plane that you get for the condition under which the brick is going to split. So, this is something we have used earlier in the Holler-Francis expressions themselves. Now, let us examine mortar and what is happening to mortar, and we understand that when we are doing a uniaxial compressive test on the mortar, it is under uniaxial compression, but in the prism under compression the mortar goes into a state of triaxial compression. So, you need to alter the uniaxial compressive strength of the mortar to be able to explain what strength would you get in mortar in a confined manner, right. So, the triaxial compressive stress, multiaxial state of stress with triaxial compression is something that we should be able to account for. And so, if you are looking at the axial compression versus the bilateral compression that you have, sigma joint x and sigma joint y, sigma jy and sigma jx, knowing that the uniaxial compressive strength of the joint material from a uniaxial test is Fj, it has been observed that the behavior that you would get for mortar if subjected to a triaxial condition in compression would follow a linear pattern. The important aspect to understand is what is the factor by which this is going to increase. So, the slope of that line is used, and this is basically based on tests that have been conducted on concrete. So, the model that we are looking at here is coming directly from concrete, developed quite early in the 20th century, and is of the form that the failure strength in compression of the mortar is an additive form of the uniaxial compressive strength plus the tensile stress, so the compressive stress in the lateral direction multiplied by a factor that comes empirically from experimental observations. So, this is the failure surface that we would use for the multiaxial state of stress in compression of the mortar. We are interested in rewriting this in terms of the stress in the joint, and therefore, it is just rewritten in terms of sigma jx with the knowledge of the uniaxial compressive strength of the mortar joint material itself. So, this basically, this last expression that you have seen is giving us literally at the point of failure, is telling us how much minimum lateral confinement is available to the mortar joint just before the point of failure. So, sigma jx is the lateral compressive stress in the mortar. So, this expression now in terms of the uniaxial compressive strength and the stress in the z direction, which is what we want to establish for the failure of the masonry assembly, is written in terms of sigma jx. Okay. So, with the failure planes for the constituents defined, if we assume that now these two phenomena are meant to occur together, that is, the crushing of the mortar is happening as soon as or immediately after the splitting of the bricks in the bilateral tension, then we use our original equilibrium equations and rewrite the expressions that we saw in the previous slide to be able to pull out an expression for sigma z now from the material constituent strengths themselves. So, from equilibrium of forces, we established that sigma Bx, which is the lateral stress in the brick into the thickness of the brick unit itself, is equal to sigma Jx, which is the stress, the lateral stress in the mortar into the joint thickness Tj, established because there is bond at the interface. Considering compatibility and equilibrium, you get that expression, and now we are able to write down the earlier expression that we had in sigma Jx in the previous slide in terms of the lateral tensile strength, the lateral tensile stress in the unit itself. So, we write the previous expression if you remember in the previous slide was in terms of sigma Jx. So, sigma Jx was pulled out from the expression, the empirical expression of the failure criterion for mortar. We use that, and with the consideration of equilibrium and compatibility, with this defined, we rewrite the expression in terms of sigma Bx. That is what is done in this particular slide. Give a factor, this part Tj by Tb, Tj by 4.1 Tb is then replaced with this alpha prime. We could simplify the expression a little. So, now we have an expression that comes from the failure criterion for mortar, and using equilibrium and compatibility, an expression for the mortar, and now an expression for the unit itself coming from the consideration of the linear failure surface in tension compression of the brick unit itself. So, this is again the lateral stresses sigma x or sigma y in the unit defined in terms of the failure stress in tension and the failure stress in compression under uniaxial conditions of the brick itself. So, you have now these two expressions which are going to be linked. Now, if you were to merge these two expressions and pull out sigma z from this, you get the at ultimate conditions, because you are considering the strength in the mortar, uniaxial compressive strength of the mortar, the uniaxial compressive strength of the unit, the tensile strength of the unit would then, and the compressive strength of the uniaxial compressive strength of the brick unit, again you get the expression in sigma z. This is the final expression that is used with respect to the Hilsdorf criterion. However, in comparison to experimental results, there is a slight deviation, and that is really because of the fact that in this we are assuming that the stress is going to be uniform at all points in the cross section, which is not the case. Stress is typically defined at a point, but here there is an implicit assumption that the entire cross section is under the same state of stress. So, that non-uniformity that is there in the distribution of stress owing to several factors needs to be accounted for. So, it is included in an empirical manner in this expression. So, this non-uniformity is actually coming from several sources. Some of these sources are you can have perforations in the geometry in the block itself, and then the dimensions of these perforations can be different. That can lead to a different state of stress in the block, in the masonry prism itself. You can have irregularities on the brick surface, and therefore, there will be concentration of stresses in some points and smaller level of stresses in other points. The mortar bed joint is again not something that is completely perfect, and therefore, again can contribute to a non-uniform state of compressive stress, and therefore, the expression that we saw in the last slide is altered to factor in the effect of this non-uniformity, and a non-uniformity factor is actually brought in. It's to be able to match experimental results in a way, and of course, this is dependent on the type of masonry that you are looking at. Some are more variable than other types of masonry. So, this value actually comes from experimental investigations on different types of masonry. You can see that if you can adopt an average value of 1.3, so a 30% correction is required. However, depending on the type of mortar and brick unit, these values can actually vary quite significantly from about 1.1 to about 2.5. So, this theoretical framework, the Hilsdorf theoretical framework, actually gives you a better physical interpretation of the failure mechanism, and is appropriate primarily because it considers the inelasticity in the material, the weaker material, the mortar, in formulating the expression itself. So, that is so we have looked at couple of formulations, one based on a linear elastic approach and one which bases itself on the inelastic behavior of the material. So, you could look at how well they are able to match experimental results. Both fairly well do their jobs in capturing the failure strength of masonry.
So, FJ and FBC are both uniaxial compressive strength?
Yes. So, yes, that is true. FJ is uniaxial compressive strength, FBC is the uniaxial compressive strength of the unit, J is of the joint material, and FBT is the tensile strength of the unit. So, the basic point is that it is an assembly of different constituents. It is a composite, masonry is a composite construction. Now, if I know the strengths of the individual elements, can I arrive at the strength of the assembly in compression? We have seen that it is not additive, it lies somewhere in between the strength and deformability of the unit and the strength and deformability of the mortar. So, the whole attempt is to be able to look at an analytical framework for it, and you have seen that it is possible to link it to the geometry. So, the joint thicknesses are what alpha prime is standing for, the ratio of the joint thicknesses. You also have that factor 4.1 that comes in here, and then the uniaxial strengths of the individual materials, compression, mortar and unit, and tensile strength of the unit. However, there is still variability, and the non-uniformity factor is something that is accounting for the variability that we are not able to capture analytically within a closed form solution itself. Okay. So, continuing, it is useful to look at in terms of stress strain curves what sort of a analytical formulation fits the stress strain curve of masonry itself. Again, we are examining compression, and in a way it is not very different from concrete in its behavior in compression, and studies were carried out a few decades ago, and they are still valid because they do a rather good job in capturing the stress strain behavior of masonry in compression. So, work carried out in the 70s, Powell and Hodgkinson and Turnsek and Kakovich are two typical initial works that try to examine what sort of a stress strain relationship do you get in different types of brickwork. They also examined, do you get differences if the bond patterns change, do you get differences if you are looking at face loaded, you are looking at flatwise compressive strength, that is a prism made out of bricks laid out in a flatwise manner versus brick on edge, and so on. So, several iterations were carried out in the configuration of the brickwork and the type of masonry units and mortar as well. However, that is the typical stress strain curve, and you can see a certain idealization of the stress strain curve is possible because it tends to be close to a parabolic shape, and here represented in terms of the ratio, the normalized stresses sigma to sigma max and epsilon to epsilon max, then makes it possible to closely relate it to the shape of parabola, and have, if you need to use it for design purposes, the equation of the parabola is very well matches the stress strain curve of masonry itself. the fact that a parabola is what is matching the stress strain curve of masonry also tells you that if you were to look at an initial tangent as the description of the modulus of elasticity and secant modulus close to the peak, let us say 2/3 or 3/4 to the peak, you will see a significant difference between the moduli defined as the tangent modulus in initial elastic tangent modulus and the secant modulus, and this is principally telling you that the material starts showing nonlinearity quite early on, right. Okay. So, with that let me move on to elements. So, what we did examine in the previous lecture and today's lecture in the beginning is the behavior of masonry as a material in compression, and the expression is a representation of the strength of the material, but you do not get the same strength in a wall, for example, and that is because you have other effects that come into the picture. So, we have now moved on from strength of the material of masonry to the strength of a masonry element in compression, and what affects the strength of walls in compression, for example, and we will again examine if there is eccentricity of your axial loads, if there is eccentricity of your compression, what sort of effects occur and what sort of effects should you be able to analytically capture if you are estimating the strength of the masonry element itself. Okay. So, the moment we look at structural elements like walls, the slenderness of the wall, the basic geometry of the wall can start inducing second order effects. We have just been looking at a first order effect as far as arriving at the compressive strength is concerned, but you will never get that compressive strength of masonry in your wall, and therefore, if you were to estimate the compressive strength of a masonry wall, you cannot use the compressive strength of the masonry and say I have arrived at the strength of the wall. You need to factor in other problems coming in from geometry, and we grossly refer to that as second order effects, but there are several aspects that contribute to the second order effects, and some of them are listed here. I would say almost exhaustive. You can have an eccentricity of the loading itself, that the load is not acting concentric, there is an eccentricity induced by the load. So, if the eccentricity is E, you already have P into E acting in addition to the P into E acting on the wall, which would mean there is a component that is just the gravity load P plus a moment acting on the wall. So, this itself can cause a stress gradient and a strain gradient in the cross section, and the compressive strength of such a wall is not going to be the same as when you are considering pure concentric uniaxial compression. So, this is typically represented in terms of the effect of eccentricity to thickness as a ratio. We talk of the E by T ratio, and we are interested in understanding what is the E by T ratio that you are examining, where does E by T sit with respect to the overall thickness of the cross section. Are you talking of E by T within the middle third, or are you talking of E by T that is outside the middle third? How severe is E by T, right? And codes would like to classify the way you deal with the compressive strength of such walls to account for second order effects into different categories of E by T. So, low E by T, medium levels of E by T and high levels of E by T, and a cap on what E by T is going to be as far as your design is concerned. And where does E by T, where does this effect come from? It is simply because your superimposed loads are not always designed to sit concentrically with the wall. You will have, because of the geometry of the construction, an eccentricity of the load transfer itself. So, code giving you a limit on the eccentricity ratio implies that you have to have construction detailing that ensures that the eccentricity is induced by the eccentricity of the load transfer by superimposed elements has to be curtailed. So, this is one of the important contributing factors of second order effects. Another aspect that definitely has a role to play is how slender the wall is, right. Now, typically codes would prescribe limits on the slenderness ratio, that is defined here as the height to thickness ratio. We are looking at the least lateral dimension. So, you take the height of the wall to the thickness of the wall, and again there are limits on what should be the slenderness ratio, because slenderness and eccentricity of loading together is going to lead to a compromise in the compressive strength of the masonry. Okay. So, we will examine eccentricity of loading first and then the effect of slenderness ratio, and you will see as we start looking at design that most codes would give you the reduction in compressive strength because of a combination of E by T and H by T effects. So, the IS code for example would give you a table which has H by T on one axis, E by T on the other axis, and you look at what is the factor by which you must reduce the compressive strength, because increasing slenderness ratios and increasing eccentricity ratios would mean lesser and lesser compressive strength of the element itself. Now, the other aspect that does have a role to play, which very often we do not give enough attention to, is you have a wall, you have boundary conditions that are the real boundary conditions that occur because of the construction, detailing and typology, and then for our calculations we idealize the boundary conditions, right. You would idealize it as a fixed boundary condition top and bottom, you would want to idealize it as a pin condition, but reality does not always have to be exactly what the idealized conditions are going to give you. Now, which means that there can be a deviation, you can actually work out some estimates of what is the rotational restraint and the translational restraint, partial restraints. You may be able to estimate those partial restraints and actually use those partial restraints to be able to arrive at effects in the wall due to eccentricity of loading or due to slenderness effects. So, this is an additional layer of complexity that would definitely come in, and therefore, first being able to idealize rather correctly what the boundary conditions should be, and if there is significant deviation from idealized conditions, being able to estimate what those partial rotational translation restraints could be is the other aspect that needs to be looked at. There is another aspect, the moment we consider the boundary conditions, the point is when you are looking at walls and floors interacting, the amount of joint rotation that you can get really depends on what is the relative stiffness of the floor and the wall itself. The joint rotation that the floor is permitting is something that can alter the boundary conditions and the deflections in the wall itself. And then of course, the distribution of the loads. Now, we are not talking of a single load, you can have multiple loads, you can have loads that are varying over the length of a wall, and that can introduce a certain difference in the estimates of the strength of the masonry wall, and together these effects contribute to geometric second order effects, also referred to as P delta effects. So, what we are going to be doing now is examining what is the role of a second order geometric effect in reducing the strength of the masonry wall, and if so, can we have a simplified analytical framework based on a set of assumptions, of course, to estimate the force displacement relationship, the P delta relationship of the masonry wall itself. So, if I know the geometry and the material strengths, can I for the geometry estimate what the strength in compression of the masonry wall is. Okay, so, that is what we are going to be looking at in this half of the lecture. The assumption, the basic assumption that we make in the in this process. Here we are looking at when you have eccentricity, there is bending in the wall, and that can basically lead to a situation of buckling. So, we are looking at a brittle material, masonry wall or masonry column, and examining the phenomenon under elastic buckling itself. Okay. For the case that we are going to examine, we are going to be looking at pin ends, which means the ends are free to rotate. That is, you might ask me, when you construct a masonry wall, how is that you get pin conditions at the ends of the wall. But typically what happens is, you have a different material on which the wall is constructed. It is not brickwork that is going to continue for the entire length of the building, entire height of the building. You normally have a concrete slab that will come in at a certain point. If you are looking at the ground story and the plinth, you might have a damp proofing course. So, you would normally have a different material at the boundaries of the wall, and because you have different material, thermal expansion coefficients will be different, and that is sufficient to cause a cracking between these two surfaces. So, you can work with the assumption that you have cracked surfaces at the top and the bottom, allowing for some rotation, and therefore, the assumption of a pinned end of the two ends being pinned is rather acceptable from the engineering calculations themselves. So, we are looking at a wall that is initially straight, subjected to eccentric loading, and examine the deflections in the wall due to this eccentric loading, and see if those deflections are actually going to compromise the force capacity, the strength capacity of the wall itself. So, if this is the wall we are examining, we have an eccentricity of the load acting on it P, and this is we assume that the eccentricity is the same at the top and the bottom. Eccentricities can be different at the top and the bottom, again depends on support conditions. If you have full support and loads coming at a certain eccentricity different from what the reaction eccentricities are at the base, you will have top eccentricity and bottom eccentricities that are different. Now, due to the deflection of the wall, because of the moment induced by the eccentricity of the load, part of the wall will crack and part of the wall will remain uncracked. Okay. So, there will be a part of the wall which goes into cracking along the height, and you call that the crack zone. This crack zone is really not going to be participating in the load carrying function. It is only the uncracked zone that is actually going to be actively participating in stress distribution. So, we have seen earlier in our introductory lecture that if the resultant of the forces acting on a wall lie within the middle third of the section, then we know that the entire cross section is in compression. But the moment the resultant falls outside the middle third of the cross section, you start getting tension, and if the material is assumed to have low or no tensile strength, you can start getting cracking in the in a material which is brittle. So, this under this assumption, it is possible that for the deflection you have cracking in some part of the wall. If the crack has to, if the entire height of the wall has to crack, it means a significant amount of the wall has thrust which is acting outside the middle 1/3 of the cross section. So, basically you need to account for the fact that part of your wall based on your calculations should have cracked, and part of the wall may be in the uncracked condition, which means you have now different cross sections to deal with as far as load equilibrium is concerned, right. So, we will keep that in mind and use that as the fundamental difference between different resisting sections of the wall itself. The wall is expected to fail when the crack zone reaches the line of thrust, and that is at the moment of collapse itself. You get a hinge that is forming at the mid height of the column, the mid height of the column itself is the location where you have the maximum displacement and expect maximum cross section to have cracked. So, let us say a significant amount of cross section has cracked at the mid height, and now the resultant compression is basically passing through a point, and when the stress level reaches the compressive strength of the material masonry, you get crushing and you can have failure. But now we are basically assuming that the mid height section is cracked, at the mid height the section is completely cracked, but the line of thrust is passing through a point which is now the hinge, and we are considering that almost 2 blocks are capable of rotating about the hinge itself and still continue to equilibrate the axial load that is acting on the eccentric axial load that is acting on it. Now, if you were to examine the wall along its height, which has some parts cracked and some parts uncracked, the deformations are going to be different, and therefore, for the cracked zone and the uncracked zone, you should actually be using different differential equations to be able to estimate the deflections that occur because of the deflected form itself. So, we will come to this aspect. You will have to consider a different differential equation for the cracked zone and the uncracked zone, and then you could solve these equations for different boundary conditions and arrive at an expression to get your load deflection curves. And these load deflection curves will actually be able to tell you how much the strength in compression of the element is going to be different from the compressive strength of the material itself. So, let us examine this. We want to calculate the vertical load bearing capacity of the wall, and these are the assumptions that we begin with. We are considering a wall of length L, unit length L, height h, it has pinned ends and it is subjected to eccentric compression. We have the same eccentricity at the top and the bottom, eccentricity represented with the notation E here. Top and bottom eccentricities are equal. So, we are basically assuming a first order eccentricity. You can complicate this problem a little more with and have E top and E bottom that are different. You will have to then account for that in the differential equations. Your deflections are going to be different based on the relative values of E top and E bottom. We assume that the material has no tensile strength, right, which means the moment you reach eccentricity, the moment you reach an eccentricity equal to the middle third of the cross section, you get the conditions for cracking, because zero tensile stress has been arrived at the extreme fiber. And a fundamental assumption here, which can become a point that you take forward and improve with a nonlinear stress strain relationship in compression. In this particular exercise, we are going to be looking at the behavior in compression as being linear elastic. To keep things a little simple, the self weight is neglected, is assumed to be very small in comparison to the superimposed load, and this is also useful as a simplification, because then you can assume that the same load P is acting at all sections. If you consider the self weight, that is going to be incrementally changing from the top to the bottom. So, this is again a simplification. Okay. So, now we need to assume, we need to start examining the cracked zone and the uncracked zone and look at developing expressions differently for the cracked zone and the uncracked zone. So, let us examine one of the sections along the height of the wall itself. You look at a generic cross section, and if the eccentricity, so if the eccentricity is going to be within the middle third of the cross section, we are looking at section 1 If the eccentricity is within the middle third, the entire cross section is in compression. So, that is the uncracked region of the wall itself. However, in regions of the wall, particularly the middle portions of the wall, the eccentricity is now going to be beyond the middle third of the cross section, and so you will have cracked conditions. So, section 00 or other sections between section 1 and the 00 should possibly have a situation of cracking. So, you have got cracked sections defined and the uncracked sections defined, and we are going to be assuming that the cracked zone is not going to participate in the load equilibrium itself. Okay, we are looking at sections along x, along the height x. Delta x is the deflection at any specific section x that you are looking at. So, there is a total eccentricity, one is contributed by the eccentricity of the load, the other is contributed by the deflection of the wall itself. So, total eccentricity E prime is E plus delta, and now since we have assumed that part of the wall section is going to be cracked and part is uncracked, we are interested in looking at what is the compressive length of the width of the compressed zone, because you can use only the width of the compressed zone in your equilibrium equations. So, let us assume that the width of the compressed zone is C and it varies for the uncracked zone and the cracked zone. So, the total thickness is T, the compressed zone, the width of the compressed zone is equal to T if the eccentricity is within the middle 1/3 of the cross section. So, if the eccentricity is less than or equal to T by 6, then C is equal to T, right. If eccentricity is greater than T by 6, then we have to then estimate what is going to be C, which is less than T. Now, for the cracked portion, we look at a triangular distribution. The width of the compressed zone is C, the total length is T, and we want to estimate what is this width of the cracked zone in case the eccentricity is greater than T by 6. So, we are looking at a triangular distribution, and the total width of the cracked zone is going to be based on a triangular distribution 3 times of T by 2, 1/2 of the thickness, minus the eccentricity of the loading, minus the deflection of the wall itself. So, we have established the width of the compressed zone for the two situations. Now, as I said, we need to establish differential equations that are different for the two cracked and uncracked segments of the wall itself. So, for the uncracked portion of the wall, the total eccentricity is the eccentricity of the load plus the deflected the deflection at that section. So, we write the differential equation in terms of EI d square delta by dx square plus P into the deflection, the total deflection E plus delta, eccentricity plus delta is equal to 0. That is your differential equation here. This E plus delta represented as omega here in your in the next set of calculations, and we are looking at unit length of wall. So, the second moment of area I is LT cube by 12 unit length of the wall. So, 1 into T cube by 12 for the rest of the calculations. So, that is the differential equation from the first expression taken forward. And for the uncracked portion, in the cracked section you have a triangular distribution. We are assuming that the material remains linear elastic. It is a triangular distribution of stresses, and the resultant is actually going to be acting at the centroid of that triangular distribution 1/3. So, it is written in terms of the compressive stress. Now, the compressive stress in the extreme fiber is considered as Fc. So, the distribution of the stresses is triangular, and therefore, the load corresponding to this triangular distribution is C, the width of the compressed zone, into Fc, which is the compressive stress at the edge fiber, half into base into height for a triangular distribution, and then you get an expression for the edge fiber compression Fc in terms of the load itself, 2 times P by C. Now, knowing the load, knowing the compressive stress, the strain in the cross section is defined merely in terms of the stress, edge stress Fc by the modulus of elasticity of the material, and having defined the stress, the width of the compressed zone and the strain, the curvature in the section can be defined in terms of curvature of that section can be defined in terms of strain over the compressed length, strain epsilon divided by the compressed length. We have now developed an expression for the strain, which is Fc by E. So, when you examine the curvature of the section, epsilon strain divided by the length of the compressed zone is rewritten with the expressions that we have in the previous two lines, which is for strain and for Fc. We plug in Fc is equal to 2p by c and plug in strain is equal to 2p by c into E into this expression, get an expression for the curvature of the section itself. So, now with the curvature established, this is essential because we know that the curvature is going to be different in the cracked zone and the curvature is going to be different in the uncracked zone. Okay. The curvature therefore in the cracked zone is now written in terms of the curvature itself. So, we defined the total displacement eccentricity plus delta as omega. So, the second derivative of the displacement as the curvature, with now the expression for curvature derived as we saw in the previous slide, is going to help us write down the differential equation for the cracked zone of the wall, right. So, with the two differential equations available, we can now proceed to work towards a force displacement relationship. Now, okay, the fundamental problem that, okay, this is rigorous because your curvature can actually be different at different sections. Can some simplification be useful? So, what is done here is we assume that the wall is cracked for the full height. Okay, this is an assumption. Of course, the wall is not cracked for the full height, but this would be a conservative estimate, and this basically helps us to keep the curvature same along the entire height of the wall. Okay, so that can help us work towards a single closed form solution for the situation itself. So, we have the expression for the edge compressive stress Fc, and then C for the cracked zone of the wall has been defined based on the triangular distribution as the expression that you see in the denominator, and from which we simplify this portion which is in the bracket and call it y as 0.5 minus E by T. So, we have an expression which is now the expression for the edge compressive stress. Similarly, for the expression in strain we use the expression of Fc by E, rewrite the expression for strain and rewrite the expression for the curvature of the section. Double integration of that curvature can give us the displacements. So, now in this particular case we know that the mid height displacement is maximum, delta naught maximum is at an x is equal to 0. You saw that the origin is at the mid height of the wall, and with the expression that we have developed for the curvature, we can actually estimate what the displacements are at different height. The boundary conditions in this case, if you were to have the curvature for all heights defined, the slope of the displacement would be 0 at x is equal to 0 at the mid height. I am looking at 1/2 of the height of the wall itself, and the displacement is going to be 0 at x equal to h by 2. So, you have boundary conditions and you can actually then be able to arrive at what is the displacement at mid height by double integration of the expression. However, this curvature profile is something that is not known to us because the cracking is different at different stages. This complication can be overcome if we assume that the curvature profile is uniform throughout the cross section. But the fact is, this is still conservative, an estimate, conservative with respect to the exact solution of the problem itself. So, if we were to assume the curvature along the height being constant, then the double integration becomes simpler. You get from the expression for the curvature at any section, plug in the values, solve it and plug in the values, and you get an expression in P. So, you get the with this simplification you are able to pull out an expression in P. You need a load displacement, finally to be able to draw the effect of eccentricity of the load itself. So, simplifying this expression by assumption of the curvature being constant along the height, you get an expression in P, and earlier we have actually written down that expression for Fc in P. So, we have two ways in which the axial load can be written. We have pulled out one from the integration of the displacement of the curvature profile, and the other one which was written down earlier with respect to the edge compressive stress. So, these two expressions, you could use these two expressions together to get an expression for delta. I need two independent expressions, one for the axial load and the other for displacement at mid height. So, you use the terms coming from P is equal to 36 by the expression that you see there, and the two ways in which the axial load has been derived. Use the two and you get a quadratic expression and get the solution of the quadratic expression for mid height displacement delta naught. So, now you have an expression for P and an expression for delta naught, and together you will be able to look at the force displacement relationship in the case of the wall with the dimensions as we started with. So, if you substitute the expression for delta naught back into P, you get the expression for the force P as you see here, and for what you can basically do, you see that this is an expression in Fc, which is the edge compressive stress, and the geometry of the wall, and it also has the modulus of elasticity. So, for a given value of edge compressive stress, if you know that the edge compressive stress Fc is the stress at which the material is going to fail. So, if Fc is the compressive strength of the material, for a given compressive strength of the material Fc, you can estimate what is the load that that wall can carry. So, the final expression has P as a function of Fc, P as a function of Fc. So, you know the compressive strength of the material, but the compressive strength of the material is not the strength of the wall because of the second order effects. So, knowing the geometry of the wall, and therefore, you can see that there is h by t that comes into the picture directly, that is the slenderness effect, and y is the one that takes into account the eccentricity. So, the eccentricity effect, eccentricity ratio and the slenderness effect together comes to reduce the force displacement, the compression capacity, compression strength of the wall itself. So, this expression and the earlier expression for delta can help you draw a force displacement relationship, knowing the compressive strength of the masonry, height of the wall, thickness of the wall, modulus of elasticity and the eccentricity of the loading itself. However, if you look at the closed form solution, and the equation is actually valid only for a certain range of y or the eccentricity ratios. So, this is basically an exercise that looks at arriving at the capacity in compression of a masonry wall, considering two important effects, the eccentricity ratio and the slenderness ratio of the wall itself.